last thing we saw was the definition of time of concentration. And this was basically, as we said, this is a time that it takes from start of the rainfall for the runoff to reach the point of concentration from all over the contributing catchment. Different approaches to estimating this, but a kind of a simplified one was the travel time, the time it takes for runoff to basically travel along the catchment and reach POC, point of concentration, plus saturation time. As long as the soil, the coverage is not, land cover is not saturated, infiltration will be dominant, and we might get no or very little runoff. So saturation time is another factor. So let's continue this and look at an example on this one, and a couple of examples, and hopefully that helps us illustrate and better understand these concepts. So I'm gonna start with this one. I'm gonna call this one an example that we're gonna look at. And this one is a parking lot. As we said last time, when we look at hydrology, it comes in all different scales. It might be several hundred square kilometer catchment type study, or a relatively small parking lot or spaces like that. So this is a relatively small one. So we have a parking lot and it has two parcels, let's say. So they're side by side. They look like this. They're both 100 meters wide and 100 meters long this way. And this is a parking lot, and they are sloped from north to south on our slide. So this one this way at a slope of 1%. The other one a little bit steeper. This one's 4%. And to collect the rainwater, we have ditches around the perimeter of the parking lot to collect the stormwater and discharge it into the stormwater sewer system. Now, let's show a couple of points here. And let's say we have a point, one right here, and another one at this point. And our POC, the point of concentration, the place where we're going to be discharging, there's an outfall or some kind of connection to the stormwater system, is right here at the bottom left corner. So that's our POC, point of concentration. And the pathway, the ditches that we have are along the perimeter, the right perimeter of the parcel, like this. And then there's a gutter at the lower end of the parking lot. So it goes down and then goes this way to the POC. And the same thing for the other one, for the other parcel, going like this. So that's basically the pathway of the rainfall, the runoff. Also, let's make some assumptions. We're going to say, let us assume T saturation is 5 minutes. Relatively low. If it's actually perfectly impervious, 100% impervious surface, it will be really zero as soon as you have rainfall, runoff starts. But let's say in this case, we have a 5 minute, not really short, 5 minute saturation time. Also, velocity along 1% slope is 0.1 meters a second. Along the 4% slope is 0.2. And along the gutter is a bit higher, is 0.4. And this is the gutter, by the way. So this is the gutter we have to collect the rainfall, the runoff. Even if we didn't have these velocities, as we saw last time, we could estimate them if we have an understanding or estimate of the cross section of the channel. We can use Manning or some kind of resistance equation and get an estimate of the velocity. But there are other ways. I'll show you later. There are tables and graphs that give us representative velocities for different type land covers and slopes and so on. And they're typically for practical purposes, good enough. And what is the question? The question is, what is the time of concentration, TC? In other words, if rainfall starts, when are we going to get contribution from the entire parking lot at the POC, which will represent our maximum discharge at that outfall? So if we're designing this outfall or connection to the sewer system, we need to have that that max, the peak discharge, and it's dependent on TC. So also gotta now looking at the two parcels we have, it makes sense based on the slopes that we have and the location of the POC. The farthest point in each of these parcels is the top right corner, points A and B. That's the farthest distance. Everything else in each parcel is the same. So the farthest physical distance will also be the farthest travel time. So that's why we're picking the top right corner, which is farthest from POC. So let's look at both of them. I'm going to say point A, the first one. What is the time of concentration from point A? So TA will be equal to T saturation. Rainfall starts, we have to saturate the surface first, so that's always there, plus travel time, TTR. Okay, I'm going to convert everything to seconds just to be consistent. So saturation time is 5 minutes multiplied by 60 seconds. That's 300 seconds plus. For the travel time, we have two pathways that we have to travel. We have to go from A to, actually, I'm going to highlight it here. We have to go from A to C, which is down here. And then we also have D here, right away. So it will be, I'm going to write it here. Travel time will be travel time from A to C plus travel time from C to POC. So two parts. And then this will be equal to, we have to travel 100 meters at a velocity of 0.1 along the 1% slope, okay? Plus, we have to travel another 100 from C to POC at a speed of the gutter speed, which is 0.4. Okay, and if we do the math, I'm going to skip the calculation, that's simple. It is going to give us 1,556. Yeah, I think I have one extra 5 there. 50 seconds. Okay, great. Let's do the same thing for point B. Point B, the same story. Time of concentration for B is equal to saturation time plus travel time. And this will be equal to the same saturation time, 560, convert to seconds. Plus, again, we have to travel 100 meters along the 4% slope. So that's 0.2. That's the velocity. Plus, now we have to travel along the gutter, but this time it's 200 because we go from D to POC at a speed of 0.4. Again, if you do the math, this will give us 1,300 seconds. All right, so what did we see? It looks like TA is greater than TB. Time of concentration from point A is greater than time of concentration for runoff from starting from point B. So conclusion, time of concentration for our entire catchment is the bigger one is the greater one, A, and it will be 1550 seconds. This is a side note we had last time. So time of concentration is not only dependent on physical distance. So in here, obviously B is farther away, but actually it takes faster for runoff to make it to POC from B compared to A. So and the bigger time, the duration is the time of concentration, in this case, TA. Okay, a very simple example, but shows us how to deal with these type of calculations. Now, one other thing that we keep mentioning is that, okay, we have discharge, we have rainfall, depth or intensity, and so on. How are these recorded and how are these measured? So typically what happens is that for measurement of rain, what they do is a actually very simple setup. It's basically like a bucket. Let's say it's a cylindrical bucket. I'm gonna try to sketch one here. So something that looks like this. And we call it a rain gauge or different terms, but it's basically a container. Has an area, a fixed area, a given area of A, and then you have rainfall, and you collect rainfall in this bucket, and then you measure the depth. The water level is going to be somewhere here, let's say. That's a water level. After you collect rainfall, and then the depth of accumulation here is the depth, the depth of rainfall. So very simple setup. One thing you will notice that, as I said it on this sketch, is that it's cumulative, meaning that we keep collecting rainfall and we keep measuring depth with time. So depth with time will change, right? So we measure depth. Obviously, it is versus time because as the rain continues, we collect more and more, so depth changes. In other words, let me write that down too. This really means accumulated depth over time. This is what we are really measuring. Accumulated depth over time. So very simple idea, but very helpful in gaining some information about this rainfall event. So how do we deal with this? How do we measure this? So let's say we're collecting data in a rain gauge in a station, and this is what we have. We have time, and then we have depth. Again, the units could be different. Depth typically in millimeters, and time typically in hours, just because of the natural phenomena that we expect. A few millimeters per hour is a typical type rain. We don't expect meters or kilometers of depth, of course. So millimeters in hours. So what happens? At time zero, you go look at this bucket and there's nothing there. So depth is zero. During the first hour, so hour one, we measure and we see, oh yeah, we have 1 millimeter of depth. The next hour, so hour two, there's some more rain, and then we measure depth and it's 4. And keep going. And hour 3 becomes 6, and hour 4 still 6. What does it mean? It means rain stopped. After 3 hours, the rain stopped, so there's no rainfall. So that's why it stopped at 6. Okay, so how do we use this and how do you interpret this? If you take this data and plot it, so I'm gonna have time on one side in hours. So I have 0 and then 1 and then 2 and 3 and 4. And then let's say depth in millimeters on the vertical axis. Again, this will be 1, 2, 3, 4, 5, and 6. And if I plot the data I've got with time, I'm going to say at time 0, there was no rain. At time 1, I had 1 millimeter. At time 2, at hour 2, we went up to 4. At hour 3, we went up to 6. And then it remained constant. And if I connect these, I'm going to get my cumulative rainfall depth graph. It looks like this. It could be in the form of a histogram, like bars. That's actually more common, but this one is also showing us what we need. Now, let's continue processing the data and see what we get. If you recall, the other parameter that we typically are interested in when it comes to rainfall is intensity. So intensity, if you remember, it was depth of rainfall over time and usually measured in millimeters per hour. If we have the depth data, as we do in this table, we can actually calculate intensity. And very simple. if we take any pair of rows of data that we have, for example, these two, we can say in this case, we had 1 minus 0 divided by minus 0, or 1 millimeter per hour of rainfall during the first hour. We can keep doing the same thing. I'm going to do that for the second hour. In this case, I'll have 4 minus 1. Remember, depth is cumulative, so I'm going to subtract the previous one to get the amount of rainfall within that last hour. So 4 minus 1. And the hour is obviously 1, 2 minus 1. So this would be 3 millimeters per hour. And so on. If you continue doing the calculations, next one will be 2. And the last one is 0 because there's no rain. Stop. Okay, let's see how we can actually plot this as well. So I'm going to plot that down here. I'm going to have the same type of plot. So this is time in hours, and then we have intensity in millimeters per hour. The same thing, we have 0, 1, 2, 3, 4, and intensity we have 1, 2, 3, and 4. This one, I'm going to use a histogram style, a bar column or bar or that kind of chart to show distribution, because it's over time. So that's a more realistic way of showing this. So I'm going to say the first hour, we had 1 millimeter per hour. The second hour, we went up to 3. So up there. And then hour 3, we came down to 2. And then last one, no rain, 0. Okay, so that would be our histogram or a bar chart of intensity. Now, just like what we did, and you noted that, we calculated intensity using depth. And the way we did it is we looked at differences divided by duration of time. That's kind of a gradient or difference calculation, which in calculus, we also call it differentiation. So what that means is that if we actually look at data, depth data, and take them, let me actually change color here, and look at variation of depth with time, delta D by delta T, that gives us intensity. In other words, if we have the depth versus time graph, which is the one I have up there, and if we differentiate, right, take the derivative, we get the intensity graph, let's call it, or chart. Just like that, if we go the other way, again, this is the inverse, right? If we integrate intensity, I, with respect to time, we get D, we get depth. So that's another kind of conversion we can look at. Physically, what does this mean? Physically, it means integral is the area under the graph. So this means if we take the I versus time, intensity versus time, and look at the area under this graph, so I'm going to say area under I versus time, we get depth, cumulative depth, total depth over time, right? That's what we're doing. But relatively simple math behind it, but good to visualize. So if you have one, the bottom line is if you have one, we can calculate the other one with good accuracy. Okay, so that's how a rain gauge is used to get some rain data. Relatively simple way, but very accurate and very representative type of data. Now, the other type of data that we very commonly deal with is that when we have flow, the runoff arrives at POC. Okay, we want to see discharge. We want to know what is the discharge there, right? So we measure discharge at a given location. So I'm going to say measure Q at a given location What is a good location to look at this runoff? POC. That's actually the definition of POC. That's where we are interested in looking at runoff magnitudes and so on, right? Um, and okay, what does that tell us? So what happens is that you're sitting at the POC and you somehow came up with a measurement device, measurement method. Like what? Put a weir, just create some critical depth control, and that's it. That's actually what it's done a lot of the time. And what you get is you're going to get on one side, you have time, again, typically in hours, and you have discharge, Q in, let's say, cubic meters a second. So we have the rainfall. We saw that in the previous slide, how it's measured and so on. But this rainfall doesn't directly turn into runoff. It might, because of a lot of reasons that we talked about, for example, time of concentration and saturation and so on, will have a different timing and peak for the discharge at the POC. And we measured it, okay, in this case, and we noticed that at time zero, there was a flow of 10 cubic meters a second. Okay. An hour later, it was still 10. So what does it mean? It means this is the flow in the river, which is what we call the base flow. So typically, especially in relatively larger streams, have flow even if there's no rainfall event. Where does the water come from? Different sources. It could be springs and groundwater. It could be snow melt, even glacier and so on. So different sources, but bottom line, you typically have some flow in the stream. There are seasonal creeks and streams that are completely dry during some seasons and some month of the year, but again, for relatively large ones, you always have some base flow. Okay. And what happens next? We keep watching and we keep measuring. At hour 2, we see that, oh, there's a little bit of increase, goes up to 15. And this continues. At hour 3 becomes 20. At hour 4 becomes 15 again. So it looks like it's going down. At hour 5 becomes 10. Hour 6, again 10. So you notice that the discharge went up because the rainfall occurred and made it to POC and went up. It looks like at 3 hours, we reached the peak at 20 and then went back down because the rainfall was stopped, right? So the same thing, if we take this and plot it, again, time in hours and discharge in cubic meters a second, and let's say we have 0, and then we have 1, 2, 3, 4, 5, and 6, and this one goes to 5, 10, 15, 20, 25. So what do we have? At time 0, we had 10. Oops. At time 0, we had 10. At hour 1, we still had 10. At hour 2, it went up to 15. At hour 3, it went up to 20. At hour 4, came back down to 15. At hour 5, went back to 10. And then remained there, looks like it. Right? And if we connect these dots, we're going to get a graph that looks like this. Right? And what's happening here? First of all, the station at the POC where we measured discharge, sometimes it's called the gauge station. Gauge, just gauge, or sometimes gauge station. And as we said, this is a hydraulic control section where you can measure depth and get discharge, typically, very commonly. There are other methods, but very common. Okay. And what did we get here? We got this graph which shows discharge with time. I think we saw this before. We've heard this term before, but this is called a hydrograph. Hydrograph. What does a hydrograph show? It shows variation of discharge or runoff, let's say, with time. Okay. What do we see on this runoff or on this hydrograph. First thing, it looks like by looking at this hydrograph, it looks like there's always been some flow in the stream even before and after the rainfall. This is the base flow. That's the one we talked about that has sources other than this latest rainfall. It could be, again, different sources, groundwater or other sources. And what happened? It looks like after 1 hour, there's a point where runoff starts to go up. Why? What happened there? Runoff from the catchment reached the POC. That's what happened. Before that, the rainfall was happening, but there was no flow, the changing flow at the gauge station. And then goes up, reaches a peak. Again, that's a term we typically use. And then goes back down to base flow. Now, you will notice that there is a kind of a space here, the area under the graph. And this one will be, I'm going to write it down here, area under the hydrograph is equal to the runoff volume. So that's the volume of rainfall we got. So the bigger this area is, the bigger the volume of rainfall has been. Okay, so let's look at a tiny example here. I'm going to say, let's say we have a catchment. Looks like this. We have the stream network. Our stream network is something like that, right? The catchment is 20 hectares in area. And there's a POC right here at this point. So that's our POC. Okay. And let's say this is the catchment that received this rainfall, right? Let's see if we can calculate the, no, okay, the runoff does not include the base flow, right? Because that is not from runoff, it's from some other sources. So it's, no, it does not include, the good question, it does not include the base flow. Okay, let's see if we can integrate and calculate the runoff volume. Now, there are different ways to estimate the shape of a hydrograph, but for many practical purposes, a simplified triangular shape is good enough. So I'm going to do that. I'm going to assume that my rainfall goes up linearly and comes back down linearly. So it looks like this. Started at hour 1 and continued to hour 5. I'm only interested in the change or increase from base flow, not whatever happened before or after rainfall. That's not runoff, that's something else, right? And then goes from 10 to 20. So a simplified shape for my hydrograph. Obviously, it doesn't capture all the details, but for what I'm doing is good enough. And then I'm going to say, okay, volume will be equal to, in this case, base 5 minus 1 times the height, which is 20 minus 10 divided by 2. It's a triangular shape. So this will be equal to, again, I'm going to skip some steps, but simple calculation will be 72,000 cubic meters. Okay, just keep in mind 5 and 1 are in hours, so we have to convert them, multiply by 3,600. Okay, and now that's a volume of rainfall. So it means over the 4 years of rainfall, 4 hours, sorry, of rainfall event, we received 72,000 cubic meters of water, basically. That's the volume. Okay, let's now convert this to depth as well. So depth over the catchment, depth of rainfall over the catchment will be, obviously, will be volume that we receive over area. So it will be equal to 72,000 divided by area, which is 20 hectares. So multiply by 10 to the 4th to convert it to square meters. And this will be, if I did the calculation right, it will be 0.36 meters of depth. So it means over 4 hours, we received 36 centimeters of rain. You could even go further, and you could say, okay, I'm gonna take 36 divided by 4 to get an average intensity. But in reality, we know that it could be, but rarely the intensity is uniform with time. It starts relatively slow and goes up and then comes back down. But if needed, we can even simplify and estimate the average intensity over time, right? So this is a typical shape for a hydrograph rainfall event. And again, some relatively simple calculations. We can go from depth of rainfall to intensity, from intensity backwards to depth, or if we have discharge measurements, calculate volume, calculate average depth. Again, we could calculate average intensity. Probably less practical and less helpful, but that could be done. Now, one thing that we haven't, and I know it might be a question now, one thing we haven't talked about yet is that, okay, we have intensity or depth. How do we calculate discharge? How do we know, oh, peak is going to be 20 CMS? How do we do that? That's what we're going to do next time, not today, but that is a maybe more practical and more helpful aspect of hydrology that we're going to get to, but we need these concepts and basics before we get there. But that will be a next step. Okay, so continuing on the idea of a hydrograph. So a hydrograph looks like this. It shows discharge, Q versus time. And it goes up and comes back down. Why? Because of the rainfall event. Rain comes in, turns into runoff, discharge goes up, and then rain stops, it goes down. A couple of kind of terms again on this hydrograph. We have the base flow, which is basically this distance, this flow that you have in the stream, even without a rainfall event. And then you have the rising limb from B to C, discharge goes up, and then the falling limb, discharge comes back down, and then you have the base flow recession, which goes back to base flow. So this is a typical shape for the hydrograph. Again, sometimes it's simplified to a triangular shape, which is good enough for many cases. Why are we interested in looking at hydrographs? Because actually they give us a lot of information about the catchment itself, the behavior of the catchment in terms of the rainfall runoff process. So what does it mean? One of the things that we already know is that the runoff depends, for a given rainfall, depends on the land use, land cover. If we have pervious versus impervious surfaces, they behave differently. And how do they impact? If you can imagine, if you have a rainfall event, given rainfall event, if you have a lot of imperviousness in your catchment, it means time of saturation is pretty low because there's not much soil or bare soil to saturate anyways. And as soon as the rain drops and falls onto the ground, it turns into runoff. So you quickly get into runoff from rainfall. On the other hand, if you have a lot of perviousness in the catchment, it's the opposite. It takes a long time for saturation of the soil and to turn from rain to runoff and so on. So in a way, this is just a schematic, but this will be a time of concentration for a catchment with a lot of impervious surfaces. And this one will be time of concentration for a catchment which has less imperviousness. You could relate this to urbanization. Why? Because in urbanization, at least traditionally, we take surfaces that were plants and vegetation and soil and grass and whatnot, and we cover it with concrete and structures and asphalt and other things which are not pervious, right? So what happens if we have this? A couple of things happen. First of all, you notice that TC1 is shorter than TC2. Also, you notice that Q peak of 1 is greater than Q peak of 2. What does it mean? It means you reach the peak discharge faster in an impervious catchment, mostly impervious, and the peak is bigger. So both of them are negative. The rain starts, you quickly get to the peak, and it has a bigger peak. So that is one of the reasons why we like to keep pervious surfaces as much as possible, even in urbanized areas, because they help decay and offset the peak, delay it, and bring the peak down, right? So why do we care? Because if you're designing a stormwater system, one of the reasons is that then you have to deal with a much bigger peak to design it for a bigger discharge, right? So that's another that's one reason. One other thing that we learned from looking at the hydrographs of different catchments is, we're going to come back to this later, but if you have a catchment that looks like this, and your POC is here, versus a catchment that looks like this, and your POC is here, if everything else is the same, slope, land cover, everything else is the same, then you can imagine that the peak from this elongated, the one with the elongated shape will be more like the urbanized impervious surface, and the one which is closer to a circle, more like the before urbanization with more pervious type surfaces, right? So again, looking at the shape of the hydrograph, we learn a lot of things about the characteristics of the catchment, and later on would be very helpful input for design purposes. So yeah, that's a lot of information received from this graph. Now, one thing that, again, as kind of basics and definitions and concepts that we need to know is that, okay, I have a map of an area, and I know that there's rainfall, and I've been asked to figure out if there's rain, uh, where does it go? What is my POC? What is my catchment, and all of that, right? It could be it could be a relatively large area, or it could be a development, a property, and somebody's looking at stormwater management and so on. So it could be, again, different scales, right? So to get into that, before we get into that, we're going to start looking at a little bit of contour maps, and then use that to do what we call catchment delineation, which means basically looking at a contour map and figuring out where the catchment is, right? So let's do that. Now, a contour map, what is it? It's basically a bunch of lines that look like this, and we typically call them ISO lines or ISO elevations or contours, or whatever terms that different references use, right? And let's say these are elevations. This is 110, this is 120, this is 130, this is 140. This is obviously a relatively simple map, but it's the idea is the same. Now, a couple of things. When we look at a contour map, a set of contour lines, they always have some curvature, and the curvature of these contour lines tells us about the slope. That's the first thing it tells us. For example, you notice that these four contour lines that we have, it looks like there's a line connecting all of them like this, which is a line perpendicular to the vertex of these contour lines, right at the vertex. And it is, if you think about it, this is a point, it is a line at which the points to the left and right are actually lower than the point in the middle. If you can imagine, the middle of this orange line is higher than both left and right. And this is the case for all of them. So in other words, this is representing a ridge. This is representing a line connecting the peaks of the topography of the top of the hills, really. That's what it's doing, right? For this, with the same logic and reason, if we connect these low points, we're going to get a swale. A swale is basically a line connecting, or valley, connecting the low points, right? So that's the first thing. If you have contour lines, we should be able to identify ridges and swales. That's step one. Okay. You might also have what we call a saddle. What is a saddle? So a little bit more complicated. Let's say we have contour lines, and these ones look like this. One up here, one up there. Then we have a couple here, and then we have a couple here, and then a couple more here. And the elevation goes from 120 to 130, here 140 and 150. So it looks like it's going up from that top to bottom. Then we have, let's say 120 here, 130 and 140. So in other words, we have almost like a focus point for a bunch of contour lines. So it's not as simple as just high points or low points, right? So in this case, if we actually cut a section like this, you're going to see that your profile is going to look like this. See, it's higher on the sides and lower in the middle. Just look at the contour values, right? And if we cut another section, a vertical one, like this, and look at this section, the same thing the opposite actually will happen. So we'll have lower on the sides and higher in the middle, something like that, right? In other words, right in the middle, this point in the middle intersection of these cross sections, we have a point where if there's a rainfall, if there's a raindrop, it's going to go like this, and then it's going to go divert this way, because look at the green line. It's lower as you go down. On the other side of the red line is the opposite. Goes like this, and then goes that way, right? So it's like a splitting line. It's a line that's splitting artificial. It doesn't exist. It's not a physical line, but it looks like it split rain. As rain it drops on this surface, it's going to be split along that red line, right? That's called a saddle, because it looks like a saddle, right? So combining the idea of saddles and ridges and swales, we can, if we have a contour line, if a contour map, we can identify our catchment. What is a catchment? A catchment is a surface that is going to receive rainfall and direct it towards POC, right? In other words, if I'm looking at this map, anything below this red line, it will be one catchment. It's going to go, rainfall will go somewhere, and the ones above the red line will go somewhere else. These are two different catchments, right? So, and the same story about the ridges. Ridges do the same thing. Swales, the opposite. In a way, their point of concentration. Rainfall concentrates along the low point, right? So let's see how we can do that. Look at this map. It is a contour map with catchment, with elevations. Now, if you notice, we have a bunch of high points. There's one here. There's another one here. And a couple there, right? Now, this line at the top is exactly like what we had in the previous slide. It's a saddle. In other words, it is separating rainfalls this way or rainfalls going this way, raindrops. The same thing happens here, the ones going this way and these ones going that way. And this line here is a ridge. It's connecting peak points. I don't have it here, but I don't have enough contour lines to the left of my image, but it looks like this is a high point. So, okay, now if you imagine, it looks like there's also a low point. I actually have it labeled as a stream, but this will be my swale. We'll continue probably going like this, and this will be the swale. In other words, all raindrops go towards the swale and flow along the swale and reach the POC. That will be our point of concentration, right? So in other words, each time we have a contour map, we can, it's not straightforward sometimes, it's not super accurate sometimes, but it's a good way of identifying the contributing catchment to a POC, to a point of concentration, right? I'll have some more examples in a couple of slides. We'll see that. One more kind of idea about stream network in a catchment is the idea of order of a stream. So what is that? So each time you have in a stream network, you have a bunch of streams, usually a lot of them actually in practice if it's a large catchment, right? And they end up at the POC, which is here in this case at the top, right? And you have smaller streams, larger streams that are generated or created by merging smaller creeks and so on. And they have come up with a way of not quantifying, but labeling these streams based on their size in a way. And the way they've done it is they look at how many streams are connected together to form that stream that we're looking at. And based on that, they came up with a ordering or labeling number. How does it work? You look at the stream, and each time you obviously start from order one. Order one means creeks that are not connected to anything else. They're basically just a starting point at the far end, the headwaters of your catchment, all the way at the top of the mountain, right? And each time you have two streams of the same order meet, they increase the order by one. So if you have two streams, order one streams merge, you get two. If you have two twos, you get three, and so on. If you have 1, 2, and 1, 1, they will the outcome will still be 2. So they have to be the same order for the order to go up. Otherwise, it will remain the same, right? So how does it help us? How does it really use? There are some empirical methods to calculate some quantities based on these orders, but we're not going to get into details of that. But this, in a way, tells us that the complicated shape and form of the catchment and stream network that you might have. For example, look at this one. This is an order 5 catchment. So this is our POC right here. And if you actually go back and do the calculations, you'll see that max order in your stream will be 5. So relatively high, right? Or you could have different numbers, right? One thing that we need to keep in mind is that the order of the catchment of the mainstream, the POC, doesn't necessarily tell us about the shape or behavior of the catchment. It just shows the complicated, how complicated network is this stream network. For example, look at this one, has order of 5, looks a relatively simple network, right? This one looks way more complicated, but the order is actually 2, is way actually smaller than the previous one. So why is that? Because again, hard to see, but if you zoom in, you'll see that it's always maybe 2 order 1s joining or 1s to 2s and so on. So we don't have 2 2s joining. That's why the order doesn't go beyond 2. So if the order is high, that doesn't mean that it's a bigger catchment or anything. It just tells us about how complicated network is than stream network. Something to keep in mind. Okay, so now going back to our contour map, I'm going to actually leave this as an activity for everybody. I'm going to show you the solution next time, or post it online. But let's say we have this contour map, and I know the labels for elevations are a little bit difficult to see, but hopefully the one on the PDF is high quality, so you can zoom in. But let's say this is our POC, and we want to identify the catchment, the contributing catchment to this POC. And I'm going to leave it to you and give you a little bit of time to do that, and then I'll show you the solution next time. But try to do that. See if you can identify the ridges and swales and saddles if you have any, and just imagine where does the water drop go if there's a rainfall, and see if you can identify and delineate the catchment on this one, and also this one. So 2 examples here, POC. And see if you can actually do that. I'll post the solution, but try to do it yourself first. And one last thing for today is that a lot of these calculations seem to be relatively simple but tedious. A lot of detailed line tracking and so on, and reading labels and so on. So something that you don't really want to do manually, as if possible, right? Luckily, there are GIS software that do this for us. There are many of them out there. ArcGIS is a famous one that you might have heard of and might have used it. At UBC, you get access to the license ArcGIS as well. But the one that I like to introduce here is a free GIS software called QGIS. It's completely free. You can download and use whenever you want, and there's no payment or license or anything. And it's very powerful. It can do many things, and I don't want to say as powerful as ArcGIS, but which is an expensive commercial software, but very for practical purposes and many cases that we might be looking at, it's really good, really helpful. So it's free and available. So if anybody was interested and wanted to look at this, obviously that's an option. This is a GIS software, meaning that it doesn't just do catchment delineation. it actually does a lot of data management and data handling. In particular, if they come in point cloud format or survey type data or LiDAR or that kind of information, GIS tools are the tools to use. They're the most efficient type of tool. So this one's free. That's why I'm introducing it here. If you haven't heard of it, might be worth taking a look and seeing if you can use it in any other places.